This is the 5th video of Chapter 2, Fundamentals of Cryptography, and here we're going to solve exercise 12 of the lecture notes. Again, the first thing that you need to do is read the exercise, take your time to read the exercise, try to solve it on your own. If you do not manage to do it, discuss it with some of your friends, and only if you have problems or you have found a solution, come again and see the rest of the video to check that your solution corresponds to the correct. Okay, so the goal of this exercise is to understand how to attack the Caesar cipher. So what I mean by the attack is that we have the enemy E that intercepts a message between Alice and Bob, and the only information that this enemy has is that they are using the Caesar cipher. It has no clue what the encryption key is, and we're going to show how to find it. Okay. The idea of the attack is that the enemy E is going to use a frequency analysis. So this is very easy. If the enemy intercepts a long message between Alice and Bob, it can just look which are the most frequent symbols that appear in the text, okay? And it turns out that in English, the most frequent symbols that are used are the blank space is the most common one, and the second most common one is the letter E. Okay, so just by looking at in the ciphertext which ones are the most common symbols appearing, you can know how the blank space and the letter E are ciphered. Okay, so here is and we're going to see if this information is enough or not to find the ciphering and deciphering keys. Okay, so we want to find A and B, right? We want to find the enciphering transformation, which, as we know, is an affine transformation on the letter, so it's of the form AX plus B, right? Let's put bars everywhere to insist that we're working modulo a certain number. Here, the modulo we're working with is modulo 9 because there are 9 letters. So we want to find A and B here, and we know two informations thanks to the frequency analysis. We know the first one is that the encryption of the letter blank, so blank corresponds to 7. We know that the encryption of 7 gives the letter D, so D is 3 here. And we know the second one is that the encryption of the letter E, so E is 4, gives letter A, so A is 0. Okay, so this is the two informations we know, and from this we try to find A and B. Okay, and let me insist on this. We're working modulo 9, right? We're working modulo 9, so do not forget this in all the calculations. Okay, so this is just a system of two equations with two unknowns. So we just need to do some computations to see if there is a unique solution to this system or not. Okay, so we just plug the expression of the enciphering transformation, and we get 7A plus B is equal to 3. And second equation for A plus B is equal to 0. Now you can use your favorite method to solve a system of two equations with two unknowns. Here I'm going to use substitution because it's quite easy. In the second one, we get that B is equal to minus 4A. And we plug this into the first one, which means that 3A is equal to 3. Okay? And the question is whether we can solve this. Well, here you need to be a little bit careful because we are working modulo 9, so you cannot divide by 3. Okay, let us insist on this here. We have that 3, the GCD of 3 and 9 is 3, it's not 1. And therefore, the class of 3 is different from 1. So 3 bar is not invertible. So you cannot divide by 3 this equation and simply say that A is equal to 1. Okay, so there are various solutions to this equation. So various A can have various solutions, various values, different values. Okay, if you really want to see what are the values for this, you just need to solve the equation 3A equals 3, and you remember that the best way to solve 3A equals 3 is to use explicitly the modulo that we're working. So this is the same as saying that 3a is congruent to 3 modulo 9, and now you can divide by 3, but do not forget to divide as well the modulo, so this is the same as a is congruent to 1 modulo 3, and therefore there are 3 possible values for a, 1, 4, and 7, okay? So possible keys, possible enciphering keys here. Keys are 1 for a, and therefore b is minus 4a, so minus 4 is the same as 5 modulo 9. Second is 4 for a, and then it becomes minus 16 for b, and minus 16 is the same as 2, and the third one is 7, and 7 times 4 is minus 28, and minus 28 is minus 1, and therefore 8. So these are the 3 possible enciphering keys that we can have, okay? So from this we conclude that the first enemy E, by just having this frequency analysis on the two most frequent letters, cannot conclude which is the enciphering key. You would just need extra information, which is not hard to find, which would be the third most common letter, okay? Good, so that was the first question. And second question is basically the same, but we have another situation, different situation. Now we know for the second person, now we have different information. So the first one is the same one. We know that the enciphering of E is A. And the second information that we have now from the enemy E prime, he has the information that point, therefore 8, gets ciphered as blank, which is 7. So enciphering of 8 is 7. Okay, and now we can again apply the same method to see if now this can be solved. So now we have 8a plus b is equal to 7, and we have that b is equal to minus 4a, so we can plug this in the first and we get that 4a is equal to 7, and b is equal to minus 4a. Okay, now we have a different situation, as you see here, because in this case 4 is relatively prime with 9, so 4 minus 1, so 4 is invertible, and you can divide by 4, is invertible. Okay, what is the inverse of 4? Well, you can either use the extended Euclidean algorithm, or in this simple case just find it by hand. So we need a number that modulo 9 is equal to 1, and you can just check many of them, and 4 times 7 is 28. 28 is 1 modulo 7, so the inverse of 4 is 7, okay? So we get A is equal to 7 times 7, which is 49. 49 modulo 9 is 4, and B is minus 16. Minus 16 is 2, okay? B is 2. So we see that we find one of these. So the correct one was the 4-2 here. This is the enciphering key, okay? The correct enciphering key is 4-2. And from this we can get finally the deciphering key. So the deciphering key, sorry, I have a problem. We have to close this a second and open it again. For some reason, sometimes OneNote doesn't work properly. Okay, I'm sharing here. So sorry for this small. Okay, so we said that we found A is equal to 4 and B is equal to 2. This is the enciphering key. And now to get the deciphering key, or the deciphering key, we just need to express the deciphering transformation, right? Deciphering key. So we know that if y is the enciphering of x, it's the same as saying that x is the deciphering of y, right? This is the key idea, okay? And now we know the first part here. We know that y is equal to 4 x plus 2 because we just found the enciphering key before, and now we can express this on the other side, which means that x is equal to the inverse of 4, which we said was 7, multiplied by y minus 2. Okay, so this is 7y, and minus 14 is plus 4. Plus 4, so the deciphering key. So deciphering key, which we usually call D deciphering key, is D equals 7, 4. Okay. Okay, so now you see that why this Caesar cipher is not used, because it's very easy to break. And there is one exercise on the lecture notes that I encourage you to do. It's quite hard, but you can try to see how to decipher, how to break the system when we're using Bijner ciphers instead of Caesar cipher.